Hello, I've had a request to do problem number 35 out of chapter 22. In figure 22.83, this one, a single circular loop of wire with radius r carries a clockwise constant current I loop equals I naught, which constrains a proton of mass m and charge e to travel in a small radius of little r at a constant speed around the center of the loop in the plane of the loop. So we're at the center of the loop. The orbit radius r is much smaller than the loop radius big R. So r is much, much smaller than r. Draw a diagram of the proton orbit indicating the direction that the proton travels, clockwise or counterclockwise. Part A. Part B, what is the speed v of the proton in terms of known quantities I naught, r, little r, m, and e? Explain your work, including any approximations you must make. C, the current was constant for a while, but at a certain time t equals t naught, it began to decrease slowly, so that after t naught, the current was I loop equals I naught minus k t minus t naught. On your diagram of the proton orbit, draw electric field vectors at 4 locations, one in each quadrant, and explain briefly. So basically, what direction is the non-Coulomb electric field going in? And part D, when the current decreases, does the proton speed up or slow down? All right. So let's get started. I'll zoom out. All right, so in thinking about the direction, so we know that the magnetic field is into the page. We know this because I naught is clockwise. So using the right-hand rule, turn into the page. Clockwise, so that would be this way. Use right-hand rule. Okay. And so we know that the proton is going in a circle. So here's our circle. We know by circular motion the force must be towards the center. So F must be towards the center of the circle. So what we're looking for then is we're trying to think about what direction V cross B must be in, because that determines the direction of the force. Okay, so let's think about this for a second. So we know that B is in negative Z, and we know that force is in negative Y for this setup here. So the question is V in negative X or is V in positive X? All right, so here's how I think about stuff like this. You can kind of do it with the right-hand rule. I like to look at cross products. Okay, so we know that if we've got A cross B, that this is equal to A2, B2 minus A3, B2. A3, B1 minus A1, B3, and A1, B2 minus A2, B1. Okay, so we know basically 0 and 0. What we're interested in, so we know it's in Y here, and we know that it needs to be a negative. Now, A3 is 0. We want the X component, and we want the Z component. Okay, we know that we've got a negative Z because it's into the page. So in order for this to be negative, then A1, which is our X component which is velocity, must also be negative. So we must have a negative V, and then that would get us that negative Y that we've already determined must be there, so then it would make sense that velocity is in that direction. That's how I think about it. There's more than one right way to approach this. Okay, so there we go. So that will satisfy our force equation. All right, so moving on to part B. So we want to look for the velocity in terms of known terms. So we need the magnetic field at the center of the loop. So B is equal to mu naught over 4 pi 2 I naught A over R cubed. Oh, geez, R cubed. This just comes from chapter 17 for the magnetic field at the center of the loop. So the force on the proton has a magnitude. Force is equal to EVB, and we know that the magnitude dp dt is equal to mv squared over r for circular motion, which we are dealing with circular motion. And this is equal to the force. Okay, so the magnitude of the force is equal to EVB, and it's equal to mv squared over r. Therefore, EVB is equal to mv squared over r. V's on both sides. EB is equal to mv over r. V is equal to EBR m. V is equal to E over m mu naught over 4 pi 2 I naught times area over big R cubed times little r. And remember, area is just pi r squared. So now we've got velocity in terms of the known terms, the r, I naught, little r, and m. Okay, so part C, now we've got a current. I'm going to read that part to you again. So part C, the current was constant for a while, but at a certain time, T naught, it began to decrease slowly. So that's actually the only part of that problem that is the most important. We've got a decreasing current. So B is into the page and decreasing. So dB dt is out, so it's going to be going in the opposite direction, and therefore minus dB dt is in. So determine dB dt. Is it going in the same direction as the magnetic field? Is it increasing? Is it going in the opposite direction? Is it decreasing? And then dB dt is the opposite way there. Okay, so therefore, we've got dB dt into the page. Put your thumb down and curl. So therefore, E and C curls clockwise, just using the right-hand rule. So if you want to, or you can draw your circle, which is what they're looking for, E and C. Okay, and so part D, is it speeding up or slowing down? The electric field is opposite to the velocity, therefore the proton is slowed down. So the trick to this problem was just to remember your magnetic field equations for a circle, and then to just sort of think logically through each thing that you know, and then you need to figure out, in terms of figuring out the direction of V cross B, what works for you. Is it the right-hand rule that works for you? Does it make more sense to look at the cross product expression and to derive it from there? And that's going to be different for each one of you. But what's important, and what I really want to impart upon you, is I want to help you learn how to do this in the way that makes the most sense to you. And my approach might be different than yours, and we might both get the same right answer. That's okay. All right, so that concludes 35 of chapter 22.